Bom dia a todos. Meu nome é Olímpio Hiroshi Miyazaki, do Departamento de Matemática da Universidade Federal de São Carlos. Bem-vindos todos ao evento Scalar Summer Webinar on PDEs. Good morning for all. My name is Olímpio Hiroshi Miyazaki from Math Department of Federal University of São Carlos. Welcome everybody to the event Scalar Summer Webinar on PDEs. This conference is a 3-day series of 45-minute talk from today to Friday, delivered by specialists on PDEs, not only from Brazil, but also for other countries. The speakers are the following: Andrzej Szulkin from Stockholm University, Sweden; Augusto Ponce, Université Catholique de Louvain, Belgium; Bojan Sirakov, Pontifícia Universidade Católica Brasil; Claudio Oliveira Alves, from Federal University of Campina Grande, Brazil; David Arcoia from Universidade de Granada, Spain; Denis Bonnier, Universidade Livre de Bruxelas, Belgium; Eduardo Teixeira, University Central of Florida, USA; Giovanni Figueiredo, University of Brasília, Brasil; João Marcos, do Federal University of Paraíba, Brasil; Lucio Boccardo, Sapienza, Universidade de Roma, Italy; Manuel Del Pino, University, United Kingdom; and Patricia Put from Universidade de Perugia, Italy. I would like to take this opportunity to thank the speaker for accepting to participate in our conference. Also, I wish to leave a few words of thanks to the member of the organizing committee, Gustavo Madeira, who had the idea of organizing this conference, and in fact, he is the chair of this conference. Odair Paiva, Adilson Presso, and Rodrigues, for hard working in the organization. Finally, for Gustavo Mauricio, for his supporting in the broadcasting of the lectures. Closing, I wish everyone to have a good conference, and I would like to invite you to be a part in the first talk delivered by Professor João at 9 a.m. Thank you very much, and welcome. Good morning. My name is Olimpio Hiroshi Miyazaki. First of all, unfortunately, Professor Bezerra Figueiredo not able to attend this conference because his wife twisted his legs, but she is now is okay. It's a great honor for me to introduce Professor João Marcos João from Federal University of Paraíba, Brazil. He will talk about k-Hessian inequality of Trudinger Moser type. João Marcos João, he is one of expert on this kind of Moser-Trudinger inequality. As in improvement or find the extremo, with many remarkable papers. For instance, in my opinion, outstanding paper by Moser-Trudinger inequality for any Laplacian in whole space. It's a very interesting paper. Welcome, Professor. You will have 4 or 5 minutes. Please, the word is yours.
Okay. Can you hear me?
Yes.
Okay. So, good morning, everybody. So we begin our talk about the k-Hessian inequality of Trudinger-Moser type. First, I would like to thank the organizer for the opportunity to talk about our work in this nice event organizing University of São Carlos. And let me say some words about the abstract of the talk. We consider Trudinger-Moser type inequality for a class of fully nonlinear partial differential operator of divergence form. Precisely the k-Hessian operator. We know that the k-Hessian operator, when k equal to 1, corresponds to the Laplacian, and when k equal to n, corresponds to the Moser-pair operator. We can see this family, indeed a family of operators that link the Laplacian and the Moser-pair operator. Trudinger-Moser inequality is about critical dimension, about the Sobolev embedding critical dimension, and this is very important for a partial differential equation in some geometric problems in limit case. And we in this situation we have a Sobolev space, and we want to prove some embedding of Orlick space, Sobolev space into Orlick space. Okay. Let me say some words how the talk is organized. In the first part of the talk, we give a brief history of the problem. We talk about the classical results on Trudinger-Moser inequality. And in the second part, we talk about new results for the k-Hessian inequality of Trudinger-Moser type. Some of the results that we present here is in collaboration with Professor Bernard Ruff, Universidade de Milano, and José Francisco de Oliveira, Universidade Federal de Piauí. Okay, this is an outline, is a Trudinger-Moser type inequality for classical Sobolev spaces. Extremal of existence of extremal for function for the Trudinger-Moser inequality. Then we consider the weighted Trudinger-Moser inequality for fractional dimensions. We have finally the Trudinger-Moser inequality for the k-Hessian, and then we discussed about the existence of extremal for Trudinger Moser inequality for the k-Hessian. This is the main result of the talk. Okay, let's say some motivations to start problems of this nature. Okay, if we see this prescribed Gaussian curvature equation involves in the right-hand side nonlinear term with the exponential growth. And this is a geometric problem that you have a two-dimensional compact closed surface with Gaussian curvature k G0, and you look for conformal metric to G0. That means that G tilde, the conformal metric, is equal to e to the power u times G0. And to find this conformal metric, you have to solve this equation. Is an example of the situation that appears naturally a problem involving exponential growth. Okay, so let's begin the first part of the paper, of the talk. It is about Trudinger Moser inequality, the classical case. So let's begin. Say some words about the classical Sobolev embedding. So in the case that we have a bounded domain, we have the classical Sobolev space W and P0, the completion of the smooth functions with respect to this norm. We know that our space, our Sobolev space, is embedded in all Lebesgue space below the critical exponent, for the case that P is strict less than n. When P is equal to n, our Sobolev space is embedded in all Lebesgue space, but not in n infinity. And when P is greater than n, our Sobolev space is embedded in n infinity. The P star, the critical Sobolev exponent, is this number, n times P over n minus P. Okay. So formally, for the case that in the borderline case, when P equal to n, we have that the Sobolev exponent goes to infinity when P goes to n. So we have this, no, our Sobolev space is embedded in all Lebesgue space. And naturally, we have the question. Our Sobolev space is embedded in L infinite space, L infinite Lebesgue space. And with a simple example, we see that's not true. With this, we get this log of 1 minus log of the modulus of x. We see that these functions belong to the space W and N 0 in the case of the ball. But of course, this function does not belong to L infinity. Okay. So at this point, we have a natural question. What is the maximum growth for phi such that if you can embed our Sobolev space into a space involving this function, say, it's a Orlik space. What is the maximum growth? What the optimal growth? This is one question that was considered by Yudovich in 61, Gorgev in 65, Piet in 66, and Trudinger in 67. And they proved that the maximum growth is of exponential type. Okay, precisely what they proved. They proved that if you have a bounded domain omega, and instead of consider the Lebesgue space as a tangent space, you consider a Orlik space, we're able to prove that for a small mu, you can embed your Sobolev space in an Orlik space where the n function associated is given by e to this power mu times t to the power n n over n minus 1. This n function. But here I have to emphasize that the coefficient mu has to be small. Later I talk more precise about that. So we have another question here. This function is the optimal growth, has the most optimal growth. Can we consider faster growth? And the answer is no. This is the optimal growth. You can see that for any high growth, if you consider a function that is faster than this one, you cannot embed this space. As you can see with this simple example, we consider this the case of the ball again, and you take this any function with gamma greater than the exponent n over n minus 1, and with this example, we see that it's not possible to embed the space in this ellipsoid associated. So this exponent n over n minus 1 is optimal. Okay, let me say about the first improvement for the Trudinger inequality was given by Moser. Moser in 71 has a geometric problem, and he has to find the best exponent beta that before I call mu. You have to find the best exponent beta, and he proved that. He proved a sharp result. He proved that for this supremo is finite if beta is less or equal to beta n, and is infinite if beta is greater than beta n. In particular, let me say that when you are in the plane, in 2 dimensions, this coefficient is exactly 4 pi. Okay. In the proof of Moser, he also called attention to the fact that the function for any fixed u, any function is integrable, but you can make arbitrarily large if you get beta greater than beta n. Okay, more improvement for the Trudinger-Moser inequality. the improvement given by Lyons. Lyons proved that if you can go beyond 4 pi, you can go beyond beta n. No? If you consider a sequence normalized goes weakly to some u in the classical Sobolev space, then this supremo is finite for any p strictly less than this number. Here we have to call attention to the following point. If the norm of u, the gradient of u, the norm is 1, you see that this fraction goes to infinity. And so you have the supremo is finite for any p, of course, because in this case you have strong convergence. And this functional that we used to call Moser functional is continuous with respect to the norm. But if the norm of u is strictly less than 1, even that we can get something better than 4 pi or better than beta n. So we have a improvement for the coefficient beta n. As said before, Lyons proved that you can, in some case, you can go beyond 4 pi. Okay. Motivated by the Lyons result, at the Drouet, they gave a improvement for the Trudinger-Moser inequality in the following sense. This is a version that was proved by Young. The Adimur-Drouet result is for dimension 2, and Young proved for n dimension. And in this version, we have involved the first eigenvalue of the problem here. So if this supremo is finite, if alpha is strict less than the first eigenvalue, and is infinite if alpha is greater or equal than the first eigenvalue. Okay, so now let's say some words about existence of extremal for the Trudinger-Moser inequality. Before, let's recall the results for the Sobolev case. If you have a bounded domain in Rn, and you consider the classical Sobolev space with P strict less than n, we know this invariant is true, as I already said, and you consider the supreme. Sorry, but over here must be P star. No, it's the power is P star. And you see that this constant is independent of omega, because the invariance for the norm, the Sobolev norm and the Lebesgue norm for P star, for the scaling, for this scaling. We know that. So consequently, the constant is never attained in bounded domain. This is a classical fact that we know. But for the amazing result of Carlson-Chang, they proved for the Trudinger-Moser case, the supremo is attained, completely different from the situation that we have for the Sobolev case. For the Trudinger-Moser inequality, the supremo is attained. They prove the result. It's a very involved proof, but just for balls in Rn. And I must emphasize the point that the paper of Carlson-Chang is the same, it was published in the same time as the paper of Lyons. And they didn't know the result of Lyons in that time. Okay. So it's true, improved a little bit the result of Carlson-Chang. They proved that the supremo is achieved for small perturbation of the ball. And after that, in 92, Fleury proved the supremo is attained for any domain in R2. And finally, Lin proved that the supremo is achieved for n domain in omega in Rn, bounded domain. No? We gave, in collaboration with De Jairo and Bernard Ruff in 2002, a new proof of Carlson-Chang result using the idea, the improvement of Lyons. As I emphasized before, Carlson-Chang didn't know that time the argument of Lyons, and we used the improvement of Lyons to give a new proof for the attainability for the case of Trudinger-Moser inequality, but just for balls. Okay, so in Young, in 2006, proved the attainability for Adimur-Drouet inequality. This one, the supreme, this improvement of Trudinger-Moser inequality. Okay, let me say some words about the proof of Moser. It is completely different from the proof of Pohojev and Trudinger. In the proof of Pohojev and Trudinger, they use the series of the exponential, and and obtain estimates for the norm of the function, uniform estimates. So this is why they approve just works for small value of the coefficient. And Moser, since he wants to prove, he wants to obtain the best exponent, he proposed a new argument. What he used the Schwarz symmetrization to reduce the problem from a omega to a ball. So instead of work with omega, he considered the symmetrization of the function and works in the ball. So you have, in this case, he used the properties of Schwarz symmetrization that is invariant in some sense. When you apply the symmetrization, you consider the ball with the same volume of omega. You have that if f is applied to the symmetrization is equal to f applied to the original function. Moreover, it was very important in the argument, the Pós-Graduação inequality. Because of the Pós-Graduação inequality, he can use he can consider non-negative functions and non-increasing. So the new inequality that has to consider is this one in the right-hand side, this one here. Has to face this one, have to prove the supremo is finite. Okay, so he gave a new change. No? He changed the variable, considered this change of variable, and transformed the problem, the radial problem, to one-dimensional problem. So finally, he has to face this one, this supremo. Prove this supremo is finite. And he proved that supremo is finite if this rho is less or equal than 1, and is infinity rho is greater than 1. Well, now, after all this change, he has to consider the space H, the C1 functions, with the non-negative derivative, and it belongs to LP space in the half-line. Okay. And motivated by the argument of Moser, in collaboration with José Francisco, Universidade Federal do Piauí, we consider a new class of Trudinger-Moser inequality, weighted Trudinger-Moser inequality for fractional dimension. So we prove a new Trudinger-Moser inequality for a class of quasi-analytic operator, which includes, in particular, the P-Laplacian and k-Hessian in radial case. And we prove that the result, we found the best exponent and proved the existence of stremal. Let me say this is the operator, the associate operator. And this operator, we can see in this here that with the choice of parameter alpha beta in theta, we see that correspond to the Laplacian, to the P-Laplacian, and the k-Hessian. But all this situation is the case that we have is radial case. Okay. So in order to give the result precisely, let me say some words about the space considered in this result. We consider a weighted Lebesgue space, motivated by what I already said, and we also consider the Sobolev space, that is the space of all locally absolute continuous functions that belongs to the Lebesgue space, and the derivative belongs to the Lebesgue space also. And so this class of spaces was studied by Opic in Köffner in a classical book, Hard Type Inequality. in this classical book, they prove the Sobolev embedding. They prove the Sobolev embedding here under these technical assumptions on the parameters. But don't worry about that. Let's focus on the Sobolev inequality. When we have alpha minus beta minus 1 greater than 0, we have that we call Sobolev case. And we have the critical Sobolev exponent, the corresponding critical Sobolev exponent. For this case, Clément, de Figueiredo, and Mitidieri, they consider a corresponding Bressis-Nirenberg problem and gave many results about this for this class of operator. They proved a similar result for Bressis-Nirenberg. And in our case, we are interested in the borderline case, this one, when alpha minus beta equal to 0. We are interested in this case. This is that we call Trudinger-Moser case. Okay, in this case, we have exactly the same situation that we call the Trudinger-Moser situation. The function space is embedded in all Lebesgue space, but not in the L-infinite space. But not in L-infinite space. So this comes again the same question. Can we find a better space where we can embed our Sobolev space? This is what we did in collaboration with Francisco. We consider this Orlick's function. This is the corresponding Moser coefficient. And we prove the corresponding Trudinger-Moser inequality. We prove that the supremo is finite if mu is less or equal than the Moser coefficient, and is infinite if mu is greater than the Moser coefficient. This was the result that we proved for the k-Hessian operator, but let me call attention to the point that is the radial case. Okay, so now let's begin to the most important part of the talk that we are talking about. We are going to talk about the Trudinger-Moser for the k-Hessian operator. Okay, let's say some words. We want to prove the Trudinger-Moser inequality for the k-Hessian in omega. We know that to consider the k-Hessian operator, we have to impose some conditions on the geometry of the boundary of the domain. This is a natural condition. And we recall that it was proved by João a corresponding Sobolev inequality for this coefficient, for this critical Sobolev exponent, corresponding critical Sobolev exponent. And also, Tian and João, they prove a Trudinger-Moser inequality for this class of operator. And our main contribution is to prove that the supremo is attained. We prove the existence of stremal for the Trudinger-Moser inequality proved by Tian and João for the k-Hessian operator, analogous to the situation of Carlson-Chan. Okay, so now I will give some words about the k-Hessian. We recall that the k-Hessian operator, of course, is related with the k-Hessian matrix. And we consider the k-Hessian matrix and the k-Hessian operator is just to consider the sum of the principal k minors of the matrix, the Hessian matrix. Another way to see the k-Hessian operator is about the elementary symmetric polynomial of the Hessian matrix, where here this lambda d2 is the vector composed by the eigenvalues of the Hessian matrix. We know that the Hessian matrix is symmetric, so we have the eigenvalues. So this is another way to see the k-Hessian. Okay, as I already said, let's recall that in the case k equal to 1, you have just the Laplacian. Is the trace of the Hessian matrix. And when k equal to n, you have just the determinant of the Hessian matrix. And this is the motion pair operator. This is why we used to say that the k-Hessian is a family of operators that you have linking the Laplace operator to the motion pair operator. And also, the k-Hessian is a divergent form, as you can see here, so an operator in divergent form. Okay, now we follow Caffarelli and Dielenberg Sprague to consider our space where we are going to work, the admissible k-admissible functions. K-admissible functions are the one that is C2 and where the Sj of u is non-negative for J1 to k. This is our space that we are going to work. Indeed, it's not a space in the linear sense. Okay, and then we denote by phi k the set of all k-admissible function, and phi k0 the set of k-admissible functions that vanish on the boundary. You see, as I said before, let me emphasize here that this set phi k0 is non-empty. What understand that we have non-zero functions if we impose the condition that the boundary of the set omega is k minus 1 convex, in the sense that we have imposed conditions on the principal curvature of the boundary. We impose the condition that the polynomial is positive. The one polynomial is positive on the boundary. So we always assume that this space, the boundary is k minus 1 convex, of course, because we want to be sure that our phi k0 is known. Okay. And associated to this space, we have the norm. We have this norm, and we have the equivalent Sobolev embedding proved by João in 94. We proved that exactly a similar result to the classical Sobolev embedding. The space phi k0 is embedded in the Lebesgue space for p less or equal than the critical Sobolev exponent k star. If in the case that the k is strictly less than n over 2, when k is equal to n over 2, our space is embedded in all Lebesgue space, but not in L infinity. And when k is greater than n over 2 and lesser than n, our Sobolev space, in some sense, not Sobolev indeed, no, but our space is embedded in L infinite space. And this is the expression for the critical Sobolev exponent. Okay, so in the case, in the borderline case, k equal to n over 2 or n equal to 2 times k, the space, the space phi k0, the space of admissible functions is embedding all Lebesgue space, but not in L infinite. Again, we are in the situation that we can use we are in the situation of Trudinger-Moser. It's the same case of Trudinger-Moser. We have a space that is embedded in all Lebesgue space, but it's not embedded in L infinite. So we have again the same question. Can we prove that this space is embedded in some better space, say Olive space? And the answer was given by Tian and Yuan. They proved that this supremo is finite, is a kind of Trudinger-Moser inequality for the k-Hessian equation. This is the nonlinear term, and here they also proved the optimal result. They found best exponent, alpha n, and beta n, related with the dimension. Where you found the capital N, indeed is small n. Okay? Just a misprint. Okay. So this is what they proved. Now, this is our contribution. We start the existence of Stremal for this supremo here obtained by Tian and Yuan. So our main purpose of this talk is to prove or give some ideas. I will not say, well, not entering details about the proof. It's very involved. We prove the supremo is attained for some admissible function, normalized admissible function. This is what we want to prove. Okay. We observe that in the case that we have dimension 2 and k equal to 1, each correspond to the Laplacian, the Tian-Yuan result corresponds to the classical Trudinger-Moser inequality. Another point that I have to emphasize here is that the argument of Moser will not work over here to start the k-Hessian case, because the norm involves not only the first but also the second derivative of the function. So we cannot use symmetrization. And Tian and Yuan propose a new argument based on a monotonicity formula that we discussed now. Okay, but before we go further, let's say that the proof of Trudinger can be used to prove a weak version of Trudinger-Moser inequality. It means that we can use the Taylor expansion of the exponential function. You can estimate the norm of the functions, and then we can prove that the supremo is finite if, let me go back a little bit, if this coefficient alpha is small enough. If the coefficient alpha is small enough. The same argument of Trudinger works for this case, but not to prove the best result, to prove a weak version. Okay, so let's introduce some notation. We consider y omega when the supremum of this functional on the admissible functions, and the monotonicity formula proposed by Tian and Wang is that if you increase the domain, you increase the supremum. It is reasonable to understand, but it's not easy to prove. Indeed, it's really very involved. They just to give some words about the proof that is really very involved. They consider part of the sum. Here we have just part of the sum. And then we consider the associated supremum. They prove this expression 20 that is a monotonicity formula for the part of the sum. And then they take the limit and prove the result. But to prove 20 is not so easy. Okay, but let's go further. Okay, we use the monotonicity formula with omega equal to a ball to reduce the problem to radial symmetric function. Indeed, Tian proved that that supremo y in the ball is equal to the supremo on radial functions. They proved this. You see, in the left side, you have the supremo for all functions. In the right-hand side, you have the supremo just for balls, for radial functions. And they prove that we have the supremo for all functions is equal to the supremo for radial functions. So we can restrict our attention to the supremo in the case that we have just radial functions. Okay, in this case, we can prove that for the radial case, we can reduce the problem for one-dimension problem, in some sense, as Moser did. No? And we have this expression 23 and 24 that relate the norm, the functional in the ball for expression in the interval, and the norm of the admissible function for a norm that, as we see, the norm in the case of one dimension. And we recall that what I already talked before, the auxiliary space, say the Sobolev space XR, the collection of all locally absolute continuous function that has finite norm, and this is the norm that we consider, and we reduce the problem to consider this based in this fact 28, 29, and 30 that we have that we can reduce our integral for the function of the f to the expression in the radial case for one dimension. We consider the norm for admissible function for the norm for the norm of the associated function in the Sobolev space XR, and we consider the new supremum. The new supremum now for the normalized function in the Sobolev space XR, and the associated functional for one dimension. And of course, we have that y star, which is the supremum that we call, the supremo for all admissible function radial. So we see that in this case, we have that the supremo y star is less or equal to the supremo LRK. Okay, you see that in some sense, we have already proved in collaboration with Francisco that the supremo in LRK is finite. And we, in some sense, we give a new proof for the Tian-Wang result. But this is not the main point that we are interested. We are interested in proof the attainability. Okay, so as I said, now we have proved that this supremo is finite. Now we want to prove the existence of thermal for this supremo. Okay. So we just recall fast what I already said. No, we have the space, we have the associated norm, and I recall the embedding, the Sobolev embedding, proved by Kaufman and Opic. See also the work of Clement and Figueiredo and Michidieri. And to prove the existence of Stremal, we use the ideas of our paper in collaboration with Jairo and Ruff, Lucio 2002, and also the argument of Carlson Chang. The argument is, in few words, that what they do, they consider the maximizer sequence for the supreme. And they want to prove that the maximizer sequence converges to a function that attain. So they have to avoid the situation that you have concentration function that goes to 0. And so they consider this S, the supreme over all normalized concentration functions in XR. And they prove that this supremo is less or equal than this constant S. After this, we show that the supremo over all normalized functions in XR is strictly larger than S. So with this argument, in some sense, we are saying that maximizing sequence cannot be concentrated function sequence. So let's consider a maximizing sequence. We have a maximizing sequence, and because the property of the Sobolev space XR, we have weak convergence, a strong convergence in Lebesgue space, and almost a very convergence. So our next step is to consider a result of Lyon's type. We assume that the limit of the maximizer sequence is non-trivial. And let's prove that supreme is attained. Okay, if the supreme is non-trivial, we are able to prove that this limit sup is finite for any p straight less than p star, where p star is a number greater than the coefficient, the Moser coefficient. And so, since we go beyond the Moser coefficient, we can prove that we have Stremal to the Supremo LRK. Okay. Let me recall what I'm saying, that I'm talking about concentration function at origin. What I understand for that? No, is a sequence satisfy the norm is lesser than 1, goes weakly to 0 in the space XR, and if you take a small interval around the origin, the complement, the integral goes to 0. This is what I understand by concentration sequence. So we prove that for this concentration sequence at origin, we prove that the supremo along of this sequence is less or equal than this number. This number on the right-hand side. It's less or equal than this number. In the next lemma, we prove that our supremo, the Trudinger Moser, for this corresponding case, the supremo is greater than this number that appeared in the lemma before. With this, what we have proved? We have proved that concentrated sequence at origin cannot be maximized sequence. So we have proved that V is non-trivial. And so we can use the Lyon's argument to prove the attainability for the supremo LRK. Now we have a regularity result that says that the V at origin is bounded in some sense. And it's very important to prove that with V, we can get a admissible function. We get V, and then we define the function U0 in this way, and then we are able to prove that U0 is admissible, and so we have completed the proof, the attainability. To prove that U0 is admissible, we have to prove first that U0 belongs to C2, and second that the Sj of U0 is non-negative for j between 1 and k. If we prove this, we have proved that U0 is admissible. We have more some details to discuss, but it's just a small thing, is not important. The main idea is this. Okay, let me say this is a blank, because the idea is to write, but in this way of show, we cannot write in this. If I use my tablet, I can write, but I will say some words about open problem. You see, this, after many calculations and estimates and so on, we were able to prove the existence of stremal to the Tian-Wang version of Trudinger-Moser inequality for the k-Hessian, but just for balls. You can see that the proof of Tian-Wang is for omega, with some geometric condition. So we have an open problem. How to prove the result for omega, any omega, with some geometric condition on the boundary. This is an open problem. Yeah. I have another open problem, but I have already in the end of my time, and so I'd like to thank you for your attention. This is some. Thank you for your attention. That's it. That's all.
Ok, professor João Marcos Dó, Thank you for wonderful lecture. Let's see, have some comments. Okay. João Marcos, only for just for curiosity, you said for result for domain different from ball. This coming from if you take operator, not radial, but a non-radial case, what do you think? I think it's the same problem, but
No, but you see, I talk about the situation, the radial situation that we proved. We did everything for bounded domain in collaboration with Francisco, but the Tian-Wang inequality for the k-Hessian operator is for any bounded domain omega, which is k minus 1 convex. This is a geometric condition that this geometric condition, I must emphasize that I have to emphasize that this is a geometric condition that is related with the space of k admissible function. There is nothing with Trudinger-Moser inequality. It is a basic assumption in order to have some admissible function. In order to avoid the situation that that space phi k0 is just the null zero function. Okay, and so we consider the situation where omega is a ball, but we don't impose the condition to that the space is just for radial functions. We can, our result works for non-radial function also, but the point is that our result works just for the ball. Our argument works just for the ball.
okay.
We don't know how to do when the domain is not a ball. So okay, there is a gap. There is a gap to complete. Is a similar situation to the Carlson-Chang. It's similar. Carlson-Chang proved they proved the attainability of Moser inequality for the ball.
Okay. Okay. I think we don't have time for another question. So thank you very much again for joining us today. We appreciate very much your talk. I hope you can see soon after pandemic. Bye.
Bye.
Thank you very much.
Thank you.
I will invite everyone to in next talk in few minutes by Professor Boccardo. Bye. Hi, good morning. My name is Olimpio Hiroshi Miyagaki from Math Department of University of São Carlos. It's an honor for me to introduce Professor Lucio Boccardo from University Roma, Sapienza, Italy. He will talk about recent development on Dirichlet problem with singular convection drift terms. Professor Boccardo, he has many remarkable papers on existence of solution, decay properties of solution, regularities of a solution for parabolic and elliptic problems. Also for problems involving quadratic gradient term. For me, the most outstanding paper is that with he did with collaboration with Murat. The title is something like almost every convergence of gradient. This result is abstract, but everybody uses this result to study P-Laplacian equation to get convergence of gradient. Welcome, Professor. Welcome, Professor. Professor, you have it for 5 minutes.
Buon dia e obrigado.
You have it for 5 minutes. Please, the word is yours.
Okay, thanks. This is my screen. The first sentence, for the first sentence of the talk, I use Spanish. Esta charla está dedicada a Ireneo, que falleció ayer. Ireneo, que era un colega, sobre todo un buen coautor, valiente, y una gran persona. Hasta siempre, Ireneo. This is the title. There are two problems. Almost all the talk concern linear problems, just in order to have a simpler situation. And even because, thanks to the linearity, it is evident to see the connection between the first one and the second one by duality. Even if the duality, if the use of the linear functional analysis and duality is not easy at all. We will see why. We are in weak sense, in weak star sense in São Carlos. We are in weak star sense in the distributional sense in Brazil. And for this summer school, summer seminar. And first of all, bon dia again, buongiorno, good morning, and obrigado for the invitation, for the organization, for all. Obrigado por saudade. And at the first time of the schedule, my talk was the second one talk after the gyro talk. So this is a picture together to gyro. Unfortunately, I was no time in order to change with the João Marcos. Dirichlet problems. Always omega will be during the talk an open bounded subset in Rn. Bounded is not so important, but it is important in order to have comparison between Lebesgue spaces to say this function is smooth, this function is not so smooth, and so on. No, in the bounded case, L infinity is a strongly a subset, a subspace of L2, L2 a subset of L1, and so on. So we have comparisons. As always, we will use ellipticity. The main actor will be a matrix bounded and elliptic. If you prefer, the Laplacian is almost always the same. I do not need smooth dependence of the coefficients, so no, I do not need Laplacian or linear operator with smooth coefficients. So since I do not need them, I will put myself in the general framework with linear differential operators in divergence form with the non-smooth, just bounded matrix MX. Then this is the framework. F of x will be always the right-hand side. A function, the function f belongs to a Lebesgue space Lm. M can be 1, can be 2, can be infinity. We will see. For almost all the talk, the last actor is a field, capital E. The field capital E belongs to Ln, n exactly like the dimension of the Euclidean space. And we will discuss the existence properties of the solutions of the two boundary value problems. The first one, the blue convection problem with the convection term. The lower order term of order 1 will be a convection term, or the second one where the lower order term of order 1 will be a drift term. That is the two problems here. The principal part is always the linear operator in divergence form, 0 on the boundary. The right-hand side F or the right-hand side G is the same, and the blue or the green, or the blue or the red terms. And we note that at least formally, with the capital M of X symmetric matrix, the two boundary value problems are in duality. At least formally, we will see. A remark, of course, boundary value problems, solution U or Psi of the two boundary value problems, of course, we understand in weak sense. That is the integral formulation. We will see in the next page. Important remark before to start is that our main tool in the study of the first boundary problem is the test function method. And I would like to recall that there are many interesting results obtained via symmetrization method. And this method does not work very well in the study of the second problem. There is a remark, roughly speaking, there is a remark we wrote in a paper in collaboration with Georgina. It is, if we try to use a nonlinear test function Psi, that is, we start with a real function phi of s, phi 0 equals 0, of course, and we try to see if the use of phi of Psi can imply some estimates in some function space. Unfortunately, it is not possible. It's not possible because, roughly speaking, if you try, you are obliged to have the condition that phi in 0 is infinity, and conversely we need the 0. It is evident that it is not clear, but it is just a telegram in order to recall that that kind of test function method works for the first problem, but not for the second. So we will try to use the linearity for the second one, at least in the linear case. But even the use of the duality is not so easy, because the duality needs clean, in my definition, clean a priori estimates. We will see. Now, the two problems in each, I will try to have each page self-contained. So I write once more the two problems, and in the two problems, there are two terms with the linear growth with respect to u, the principal part and the lower order term of order 1, without any sign condition, like if we deal with the lower order terms of order 0. So the problems, it is not evident the coercivity, and even more. A formal approach says that it is possible to have coercivity and use the existence with the Lax-Milgram, very easy because the problem is linear, if the size of the norm of capital E, the norm in Ln, the norm of capital E is small enough with respect to the ellipticity constant and so on. Or if the divergence, this is a mistake, not the norm, the divergence of E is 0. In that case, there are no problems, because or with a small norm or divergence free, E is too easy, it always is done. So we are interested in the general case, no restriction of the divergence, no divergence free, no small norm of capital E. To the papers of the first time of the study of the problems. In the first problem, as an invited paper, recalling Guido Stampacchia, is more studied the first one. In the last paper, the second one, and the paper of the middle, there are more general contribution, mainly for non-smooth coefficients. Once more, the assumption, I repeat, now I point out only the first problem, the convection problem, and I repeat omega, the ellipticity, the right-hand side belongs to Lm, and capital E is a vectorial field in Ln. So, the definition of solution for the first one, but also for we have a weak or distributional solution if U belongs exactly to the energy space W1 to 0, and we have the integral formulation for every test function V which belongs to W1 to 0. Or, in some cases, we will see, when we do not have enough information about the summability of the right-hand side of fx, it is not possible to find the solution W1 to 0, even if capital E is 0. Then we will find the solutions outside of W1 to 0, in some Sobolev space, W1Q larger than W1 to 0, and so the test function will be smooth functions V. Okay? About the framework, the meaning is it is of course a classical framework about weak or distributional solution, but I point out a remark of the coercivity. If I use V as test function 2 times, so in order to use Lax-Milgram, we do not have a sign here, so here plus or minus the same. Here we use the ellipticity, and here we use minus the elder inequality with the 3 factors. And then we use here Sobolev bending. We have 2 times the contribution of the integral of the gradient to v to the square. The first time with the constant alpha, the second time minus the Sobolev constant and the Ln norm of capital E. So if capital E is not too large with respect to alpha, we have coercivity. If not, not. Our work is to study any capital E in LM, even with the norm large. Okay, the green box say okay if capital E is not too large. We will study the general case. I repeat once more, thanks to the previous pages, that all is easy if divergence of E is 0, or if the norm of capital E is small. The first result I proved more than 10 years ago is the so-called Stampacchia-Calderon-Zygmund theory for the 2 problems, the black problem, convection problem, or the red problem, the drift problem. Again, the framework, and I repeat, I proved the Stampacchia-Calderon-Zygmund. What is? It is very easy to say the result proved for the black boundary problem above or the red boundary problem are exactly the same of the case capital E equals 0. The capital E equals 0, where for M is the index of summability of the right-hand side f of x, where, or G, where for M large enough are the Stampacchia summability results on the solution U, and for M small are the Calderon-Zygmund results if M of x is smooth. And if M of x is not smooth, the result that I proved in the past century in collaboration with the Thierry Galouet. And here are the results. The results are here. And for M large enough here, we have existence of W1 to 0 solutions. And the solution U belongs to L M star star. M star is the Sobolev conjugate of M. M star star is the double Sobolev conjugate. And you have this kind of information. Then for M small, we have the existence in W1 M star, the Calderon-Zygmund result for, I repeat once more, is exactly the same as the result of Calderon-Zygmund. If capital E is 0, M with the smooth coefficients. M equal to 1 is a little bit different, is the third statement. In the third case, the Lebesgue framework is not completely correct in some sense. Is more sharp the Marcinkiewicz framework. And then we have once more I put the existence of the solution. Only there is a gap here. The M strictly less here. What is the situation if M is exactly equal n over 2? I will say in 1 minute. And the last case, if M greater than n over half. M greater than n over half, I proved 10 years ago that we have bounded solutions, like in the case when capital E is equal to 0, but we need not E capital E in Ln, but we need E in Lp with the P strictly greater than N. I have also got this. And this borderline case I studied just last year. It is possible to prove exponential summability, but once more with capital E more regular than Ln, in Lp with the P strictly greater than N. And there are counterexamples that cap E in capital N and F in N over 2, it is not possible to have exponential solutions. A solution with exponential summability. Okay, I would like to point out one point of the previous theorem. I repeat here the first two cases. The second one is the less regular case. We see that since the function m star, recall the definition of m star, the Sobolev conjugate. M star is an increasing function of m. So in this red case, we have not regular, very singular solution. Nevertheless, for m increasing, we have the summability of the gradient in Lm star. So if the summability of the right-hand side f increases, the summability of the gradient of u of the solution increases because Lm star in the more singular case. And in the first case, that is, it is possible to have a Calderon-Zygmund aspect even in the first case, even if capital E is 0. So we are exactly in this simple case, the principal part and the right-hand side. I proved in a paper dedicated to the 70th birthday of Andrzej, capital E equals 0, I repeat, that the red result that here is proved for m between 1 and 2n over n plus 2 is false, is not true for m greater than n over 2. It's not true. And we have, so, and I was able to prove that the result is false for m greater of n over 2, but I am not able to prove that the result is false. I'm not able to prove the result is true if m is greater of 2n over n plus 2 and less of n over 2. In this case, I am not able to prove even for capital E equals 0. I am ready to beat some beers that the results is always not true, but I am not able to conjecture is the result is not true. Of course, not exactly here because there is Meyers, but okay. And I discussed, I presented the results for the convection term, the convection problem, for the drift problem, exactly the same. It's very easy to repeat that for that problem, the existence, the properties of the weak solution Psi are exactly the same of the simple case where capital equals 0. And I proved in this paper of 2 years ago, using a little bit, it is difficult to understand at this center, a little bit of the duality. Not the duality complete because the a priori estimates, the inequality proved for the first problem are not linear, even if the problem is linear. So now it is difficult to use in order to have the existence of the red problem. But can be a small starting point. Nonlinear principal part, completely different framework, studied 1-2 years ago in collaboration with my Sicilian colleagues Rita Cirmi and Stefano Bucheri. What is the method in order to prove the existence? It is quite strange because our problems are linear, and the starting problem, the approximate problems, are non-linear problems. Even if the nonlinearity is quite soft, we have on the inside of the divergence u, and we replace u by the ratio un over blah blah blah. So for every small n, we have a bounded nonlinearity. Of course, the nonlinearity is not uniform with respect to n, but we can start. And there are some problems in order to recent problems studying that kind of things. There is one devoted to the nonlinear principal part. There are two papers devoted to parabolic problems. The first one I forgot to write here is a very recent paper accepted 2-3 days ago in collaboration with Orsina and Porzio. And I go back now quickly to the Liti case. There are work in progress about unilateral problems, always with Rita Cirmi and José Francisco Rodrigues. Just a few words. When capital E does not belong to Ln, an important case is the case where 0 belongs to omega and capital E looks like a constant over modulus of x. So just for nothing, just for epsilon, in this case, capital E does not belong to Ln. Capital E belongs to every Ls Lebesgue space for every S smaller than n, but not L. Okay, in this almost almost radial case, not radial of course, but almost radial, understand me, because capital E is less than something which is radial. Not radial, sorry, but in some sense we have explicit information that we can compare with radial examples. And we are outside of Ln just for nothing, I repeat, and our framework changes completely, and our framework, our results strongly depend on the size of the constant capital A. And there are here, I will put a list of results. It's not important exactly, but there are explicit and sharp estimate on the size of capital E with respect to the summability, the existence of the solution. And I would like to say that in the proofs, I strongly used inequalities that I study. Ireneo was my teachers in the general framework in order to understand that kind of situations. And then I developed without Ireneo, of course, yeah, but okay, sorry. This is the complete list of the results. You can see that depending on the size of A, we have something, but it is just a list. Radial examples are important in order to say that the previous list of results is sharp. It is possible also to have a completely very, very singular vectorial field capital E, completely outside of capital N, like in L2. But if a capital E belongs to L2, we need a completely different functional framework. Even the distributional solutions are not enough. We need to use a framework introduced a quarter of a century ago in a paper in collaboration with Philippe Benilan, Thierry Galouet, Juan Luis Vasquez. It's too complicated to recall now, but I use this framework in order to study the possibility of the existence of solutions very, very singular, very, very non-regular, when capital E belongs to L2, in a paper of 5 or 6 years ago on GD. And I would like to point out the basic estimates if the starting point is this nonlinear problem. I repeat once more, this is a little bit strange to the approximation of a linear problem with the nonlinear problems. Now I go a little bit quicker, and I recall the red Stampacchia truncation or the blue GK function due to the Giorgi. And we will see that the first estimate concerns the truncation at any level. And here we do not need, where Fn is a sequence of smooth functions converging to F, En smooth vectorial field converging to E. And we will see that we have an estimate, and depending only on the L2 norm. Even in the case, in the general case, when we use the Ln assumption on the summability of capital E, for the basic standard estimates, we need only the L2 summability. I repeat in this page part of the previous page. The second estimate is even more. We have an estimate of the sequence UN in a strange form. We are not able to have an estimate of UN in a Sobolev, in some Sobolev space. Recall that 10 minutes ago we discussed a little bit about non-coercivity. We have a sort of very, very poor summability. That is, we have an a priori estimate on the Sobolev space, on W120, but not of the sequence UN, but the sequence of log 1 of UN. Very, very poor estimate. An improvement, a recent improvement, here we need L2, in general Ln, if we have on capital E a summability of order n, r greater than 2 and less than n, we have this result on the middle, poor, and always poor result. About the results concerning the first problem or the second one, I would like to recall a result of 1 year ago. That is a weak maximum principle. Always we have capital E belonging to Ln. We have the nice W120 framework, so we assume on the right hand side F summability or order to n over n plus 2, and f of x is greater or equal than 0. Of course, not 0. It is not trivial, but not so difficult to prove that the solution u of x is greater or equal than 0. But we don't know at that moment the size. This result is not so difficult, but not trivial. We proved independently Thierry and Louette and myself years ago. But more information. More information is the theorem that I proved 1 year ago and dedicated to a birthday of a friend. And the result is the following one. We can say that the function u, it is possible perhaps that the solution u is 0 on some subset. But if u is 0 on a subset of omega, then this subset is a subset of a zero measure. This is the result. So weak maximum principle. Of course, an open problem is it is possible to say more. With the same assumption, it is possible to say that if u is 0 on a subset, then this subset is a subset of zero capacity. I don't know if it is true. I don't know counterexample. Or it is true with some more stronger assumptions. I don't know. However, at the moment, weak maximum principle is always a good result in order to understand the situation. Once more, it's strange that in the proof for the existence, we need the capital E with the Ln summability. For the proof, we need only L2 summability. We need less. And then the open problem that I discussed 1 minute ago. For the drift problem, we have exactly the same statement. The proof is a little bit is quite different, but the result is the same. And here we do not use the duality. Now, a little bit quicker, that kind of tools can be used in some elitist systems that I studied 7 years ago for the first results. Last year in collaboration with Georgina. If we add a lower order term of order 0, the situation changes enough because and I presented that kind of simple situation with the same results, but with the simple situation in the PhD course in the Università Complutense in Madrid 1 year ago, 1 year and a half. Why? I will be quickly, because in this case, we start with this blue inequality estimate. Blue estimate is poor, but not so poor like the log case. It is very important in order to have the existence proof. And we will present here just a case in order to have the existence exactly in W120 with the classical assumptions on the right-hand side. We put UN as test function, and here we use just Young inequality, this term with the coefficient alpha over 2, and the second one. It's completely self-contained. Then we use we have alpha over 2 Sobolev, and for this term we split in two when UN is less than the modulus of capital E is less than rho, and where the modulus is greater than rho, we will use rho. And then here we use Elder inequality. Here, this term is exactly this one, but the red factor can be, we can say that the red factor is small if rho is large because of the absolutely continuity of Lebesgue integral. So we put all together here, a copy, and we put all together this red contribution I I define omega of V this one, which is small for low range. And so we have exactly this inequality, very, very simple. And then we use interpolation. We use interpolation between 2 and 2 star with the basic point L1 here, because we can use the inequality that I presented 2 pages ago. The norm of UN in L1 is smaller than norm of F in L1. And so we put all together, and we have here UN star even on the right hand side, but on the left side we have the integral with the power 2 over 2 star. Here we have on the power 1 over 2 star, and here we have to the power 2, sorry, 2 theta, and 2 theta is less than 1. So we have the proof very simple here, and without the trouble, that UN is bounded in L2 star, and then in the Sobolev space W1 to 0. So we have the existent weak solution. It is very easy to pass through the limit, and mainly we have this inequality, sorry, the star inequality, where the inequality is very clean, thanks to the presence of this term, the zero order term. In my first paper of 10 years ago, the a priori estimates was not clean, was a little bit implicit, so difficult to use. It is very, very simple. The constant, of course, we do not have an explicit dependence with the rest to capital E of the constant C of V. Nevertheless, this form is a nice form in order to use the duality for the study of the drift problem. Okay? I repeat, clear inequality. It is possible to here we have the lower order term with the coefficient 1 here. We can have L1 coefficient, but strictly positive. I have no time to discuss. Always with a nice estimate. The drift problem, it is very easy to study thanks to the clean estimate of the previous problem. Okay, I need to go quickly. Here I presented the direct study of the duality, no? Because we had the first one, the second one, for every test function V, for every test function W, we put in the first one V equal the solution of the second one, and in the second one W the solution C of the first one, just the standard linear functional analysis duality, and we have the estimate. I repeat, this is important, an important achievement thanks to the new proof, and the new proof uses strongly the zero order term. Another problem and so on. I have no time to discuss this one with interesting, because the drift problem with very singular drift problem, very singular if the right hand side, however, is a bounded function. It is possible to develop for the study of Hamilton-Jacobi. And now I use the last minutes in order to discuss something which is a little bit surprising for me. And this one. We start with the capital E equal to 0. And I recall a result in collaboration with David Arcoya on a paper Journal Functional Analysis 7 years ago. We assume that even if A of x is singular, just an L1 coefficient, if we assume that the right-hand side f of x, please look at the first line in the case capital E equal to 0. with Arcoia, we studied just the basic case. And you assume the Q domination, this is the last line, the assumption in the last line. F of x is bounded by a constant times a of x, exactly the coefficient of the zero order term. Is an assumption, the control of two terms of the equation. Of course, an assumption is an assumption quite natural in the radial cases, for example, but even in general, it is a reasonable assumption. And we proved that this assumption, the star assumption, implies the existence of bounded and W120 solution. Is a scandal because with the right-hand side, the F, which belongs to L1, we have a bounded solution. With the right-hand side, the F, which belongs only to L1, we have a finite energy solution. So two scandals. And it is the strong force of the Q assumption, the Q domination, the star assumption. The idea is very easy, it's formal. Use the GK function. You put GK of x. I repeat in the, and now I repeat the approach with the Arcoia, even in the drift case. The drift case is very easy to see. Conversely, the convection term is not easy to see. It's strange, the two problems are in duality. When the convection problem is a little bit more easy, the second one is more difficult, and so on. You put this type of problem, and then we have the right-hand side, G is there. And there we used the Q assumption here. And the contribution of A of x, T of x with that kind of test function. But the type of test function, we have you put the test function GK of psi. But at that moment, with the multiplication, gradient of psi is exactly the gradient of GK of x, because where is 0 is 0. So you use the Sobolev inequality and the Elder inequality, and you have this situation. If K is greater than Q, we can drop the second black term, and we have just the first one and the last one. We can cancel, if it is possible, be careful, we can cancel, and what is the situation? We can cancel, but after cancellation, we have alpha, the ellipticity constant, less than this integral. This integral, once more for the absolutely continuous, the Lebesgue integral, is small for k large. So we have a contradiction. And the contradiction is that you cannot simplify here. Not simplify means that GK of psi is 0 for k large enough. That is, psi is less than q and a constant k dependent here of capital E. Very simple presentation thanks to the assumption introduced with Arcoia for the drift problem. In convection problem is not so easy. It is important to work enough. I wrote recently a paper with example and counterexample with proofs. Proofs, example and counterexample. It is a recent paper accepted just a few days ago on ESAIM, and it is a paper dedicated to the 60th birthday of another friend, Enrique Zuasua. Obrigado. Thanks. Ciao, grazie.
Grazie. Thank you for this wonderful lecture. Now, let's see, have some questions. Yes, they appear here from Gustavo Madeira. Very nice talk. Can you read here?
What you mean by double phase, please, exactly? Sorry, I have a... Sorry?
So,
Come?
like PQ Laplace.
You mean the general situation with the drift problems? Allora, the P-Laplacian, in some sense, even more general. P-Laplacian framework we studied in a paper Nodea 1 year ago with the Cirmi and Bucheri. For the PQ, we have double. I don't know exactly. It is very difficult to discuss without voice. I ask to you a direct contact in order to discuss a little bit, because I'm not so sure that I understand the point. Conversely, I think that is interesting, at least to check if the Q assumption that introduced with Arcoya in this framework can produce bounded solutions or not.
Okay, thank you. Let's see if he has another question. No, I think yes, okay. No question. I have a, let's see if we have it. I have a one question, but just for curiosity. About capital M is the hypothesis on capital M. It's only positivity, or need to put more?
You mean in the result, the result concerning a weak maximum principle?
Yes.
Greater or equal to 0, of course not 0. For example, important example, f of x is the characteristic function on a subset strictly contained. So that is, f can be 0 on a set of positive measure. Nevertheless, the function u, if is 0 on a subset, the subset f is a subset of 0 measure.
Okay. Thank you. More question? I think no. Thank you, Professor. Thank you very much for joining us today. We appreciate very much being here. I hope you see you personally after the pandemic.
I repeat. My presence was in the very weak stars. I use a linear functional analysis vocabulary. I am there in a weak star sense. I hope at least in weak sense next time. Not weak star.
Okay, thank you very much.
Okay.
Obrigado. Okay. I will invite everyone to the next talk in few minutes. By Professor Andrzej Szulkin.
Good morning, everyone. For those who join us, welcome. My name is Francisco Dai. I am Associate Professor at Federal University of São Carlos, and it's a great honor for me to present Professor Andrei Zukin from University of Stockholm. Professor Zukin has been an expert in topological and variational methods for nonlinear analysis, developing new ideas and techniques, in particular with applications on nonlinear elliptic problems, many of them related to the Schrödinger equation. He's going to talk about a Sobolev-type inequality for the Q operator and ground state for the QQ equation with critical Sobolev exponent. Welcome, Professor Andrei Zukin.
Thanks.
Thank you for accepting this invitation to take part in our webinar. Now I would like to hand over it to you.
Well, can you see the slides?
Yes. Not now.
You don't see them?
No, I can't see. It's black. Now it's okay.
Now it's okay. All right.
Yeah.
So I can. Well, first of all, I would like to thank the organizers for inviting me to give this talk, and let me also say that this is my first talk on a remote conference. So let's see how it will work. So I will speak about the curl operator and a curl equation and its connection with some kind of Sobolev inequality. And this is joint work with Jarosław Mederski from Warsaw and what I will speak about is, well, first of all, perhaps I will start recalling a few well-known facts. So we have a domain omega, well, everything will be in R3. And then the Sobolev constant is defined as infimum over this quotient. And it is very important if one looks at solutions to this equation. And what is also known is that the Sobolev constant is independent of omega. It can be attained only, or it is attained only if omega is the whole space R3. And the infimum will be taken by ground state solutions to this equation. And they are called Aubin-Talenti instantons. And also let me briefly recall that D1 to 0 of omega is, as usual, the closure of C0 omega with respect to the L2 norm of the gradient. And D1 2 will be, of R3 will be functions U in L6, which have a finite L2 norm. Also, a very well-known fact is that D12 of R3 is equal to D120 of R3. So one can approximate all functions by functions of compact, C-infinity functions of compact support. What I want to look at today is to find some constant which I call S curl, and it should be the infimum of some quotient, but I want to replace the gradient U by the curl of U. And also I wanted to have the property that it is attained by ground state solutions of this equation. So instead of having the Laplacian, we have here curl. and one needs an appropriate function space. I will come to this later. Now there is one obvious candidate. Simply replace the gradient of u by curl of u. But this doesn't make sense because curl of u is in fact equal to 0 for some u. In fact, the kernel of curl is infinite dimensional. So one needs to find something else. Well, before doing that, I would like to give a physical background for why this problem is interesting. So we start with Maxwell's equations. One has in a dielectric and non-conductive, non-conducting, non-magnetic, and charge-free medium. And these are the four Maxwell's equations. Well, if these assumptions are not satisfied, there will be some further terms in this equation. And here E is an electric field, B magnetic field, D is electric displacement field, and well, this is vacuum permittivity is a physical constant. C is, of course, a speed of light, and P is a polarization. And polarization appears via the constitutive relation, which reads D equal to epsilon 0 E plus P. So, and now what I will be doing here is that I take curl of this equation. So we will get the t derivative of curl of B, and curl of B is equal to this. So the equation becomes curl E equal to minus gradient of the t derivative of B, and now inserting the right-hand side of the second equation, second Maxwell equation, we get this. And after using the constitutive relation, we get this expression. And also, one knows that curl E is equal to the minus Laplacian of E plus gradient of the divergence of E. And now collecting terms, we can rewrite it in this way. Now, if there is no polarization, if we have P equal to 0, then del times E is equal to this, and we know that del times D is equal to 0. In other words, this will be 0. So we have minus Laplacian E, and now we have plus this. So we get the usual wave equation, so this is not particularly interesting. But now let us assume that we have, well, first we will be looking for time harmonic electromagnetic waves. One can think of, for example, of light waves of a single frequency. And then we have thick E equal to usual E to the power EI omega t. Omega is the frequency. And then the equation or the system of equations looks like that. And next we assume that the polarization is proportional to E, but this constant of proportionality is dependent both of X and of E squared. This is called the dielectric response function. And typically one takes epsilon equal to this. And now if the light intensity is small, then this term can be neglected and we get a linear system of equations. Another case which has been considered by physicists is that P is equal to 4, and this is called the Kerr nonlinearity. Now all this makes it reasonable to consider a more general equation. So we have curl E plus some V of x E equal to small f x E. So E goes from R3 to R3, and small f is E derivative of capital F. In fact, in what follows, I will always have V equal to 0. So now there are some special cases. When one is that if one makes a so-called scalar approximation, that is, one neglects this term, or alternatively one can impose cylindrical symmetry, which may have may look like that. And in both cases, one will have that curl E is equal to minus Laplacian of E. And then one can, this will be a semilinear system of Laplace equations. Now here, to make a scalar approximation, this is considered often by physicists when considering waveguides, but the problem is that sometimes one gets solutions which are not physical. So this reduced problem has been considered first by stewards and co-workers in the 80s, I think, and then by those people you see in 2006. And the full curl equation, well, it has been, to my knowledge, it has been treated first time by Bartsch and Medersky in this paper. And now let me look a little bit more carefully at this equation. Well, first of all, formally the solutions will be critical points of this function of J, and it is always assumed that F is strictly convex in U. And this is, in fact, it will be very important for the proofs. And if F is not convex, and there is no possible reduction to the Laplacian, as far as I know, there are no results at all. So now, if U is, written like that coordinate-wise, then one sees that the quadratic part can be written either like that or like that. And here one clearly sees that that if dj ui are equal to di uj for oi and j, then this will be 0. So now one can decompose U into two parts, V and W. The first part is divergence-free and the second part is curl-free. And for W, we know that W is equal to, in R3, W is equal to the gradient of some scalar function. And therefore, we can write curl U squared, integral curl U squared equal to integral curl V squared. And this is in fact equal to the gradient of V, integral gradient of V squared. So one sees that the kernel of the quadratic form consists of W, which are equal to the gradient of something. So the kernel is infinite dimensional. And this makes, in fact, the problem difficult to treat. So now to define a function, a space of functions on which J can be considered and of class C1. Well, what space to choose depends a little bit on how what F is. And here I will concentrate on capital F equal to 1/6 U to the power 6. So this is, since we are in 3 dimensions, this is the critical Sobolev exponent. And we consider this problem. Now we take omega, a domain with smooth boundary, and well, the first space is, I call it W6 curl omega. These are functions in L6, such that curl is in L2. And the natural norm is this. We take L6 norm squared plus curl U L2 norm squared. And also another function which we will be using is W06. And as expected, one takes the closure of C0 infinity in this space. Also, as is the case in the usual Sobolev spaces over Rn, we have this identity. Now I will need 2 subspaces of this space X or W06. We take first OV, such that V is L2 orthogonal to all functions or all C0 infinity functions whose curl is 0. And W omega, we take functions which are still in W06 and which have curl 0. And now note that locally one has, well, curl phi is 0. So locally phi is a gradient of something. And then using this and inserting here, one easily sees that the divergence of V is equal to 0. And in particular, curl V will be equal to the gradient of V. And now we let omega be equal to R3. Well, first of all, then W is equal to the gradient of Z, as I already mentioned. And we have, one can show there is a Helmholtz decomposition. X is equal to the direct sum of V and W. So we have divergence free part V and curl free part W. And an equivalent norm, it's quite natural to define it in this way. Also, V is a subspace of D1, 2. And now let me define S curl omega, which should be a kind of substitute for the Sobolev constant S. So I take U equal in a W0 sex curl omega, and then I can extend it by 0 outside omega. And S curl omega will be the largest constant, such that this holds for all U which are here but not in W. Although one can in fact also take W, because if U is in W, one can take V equal to minus U. So if one wants, one can remove this. And next, what we need is to look at this integral. And here U is fixed, and for fixed U, it is easy to see that there exists a minimizer. And if I call it W of U, and it has been shown by Medersky that in fact it is continuous from L6 to L6. So therefore it's possible to characterize S curl of omega. Well, we take, instead of taking O W, we take W of U, and then we take the infimum here. In fact, here U cannot be in W because this would give 0 by 0. And now, if I define S curl, I just remove R3 to shorten notation. So we have a lemma that S curl is strictly larger than the Sobolev constant. Well, the first part to show that S curl is bigger than or equal, it's quite an easy calculation. But in fact, to show that there is a strict inequality, one must use the fact that S curl is attained. Perhaps one thing that I would like to come back to and point out is that here we take U supported in omega, but we still take all W which may not necessarily which may not be supported in omega. So here W are in R3 and not necessarily in omega. Well, I will come back to this point. If I'll have time, I will come back to this point at the end of the talk. So now, next theorem which I want to discuss is that S curl is independent of omega. Well, first of all, since these functions can be extended by 0, we have this, and then it is clear that S curl is less than or equal to S curl of omega. And the reverse inequality, in fact, is tricky to show. Well, now I want to outline the proof that S curl is attained in R3. We have this decomposition and V divergence free, W curl free. And now the following result will be needed. It's a part of a more general concentration compactness principle. We take a sequence Vn in V, which Vn goes weakly. We assume Vn goes weakly to V0. And then passing to a subsequence, we have the W Vn goes weakly to W of V0. And also W of Vn goes to W V0 almost everywhere in R3 and in LP log for p less than 6. Note that W is our functions in L6, so weak convergence doesn't imply almost everywhere convergence, but for V of W of Vn, actually it does. And now the idea of the proof. Well, first, of course, since recall that V is contained in D1, 2. So if we pass to a subsequence, we get Vn going to V0 almost everywhere. And also in the space of bounded measures, we have that gradient Vn squared go weakly in the sense of measures to some measure mu, and this goes to weakly to some measure rho. And also we have an at most countable set J and non-negative weights V such that, well, this is Pierre Lillion's concentration compactness principle. Well, we will not need this, but we will need this equality. And here we have that Vn is bounded. This implies that Wvn is bounded, so Wvn goes weakly to W0, to some W0 after taking a subsequence. And now a crucial observation here is that J is an at most countable set, so we can find an open set Ek with arbitrarily small measure. And if we take a ball of radius r, we can use the fact that Vn minus V0, when Ek is removed, we have weak convergence well, excuse me, just the opposite. Since we have removed Ek, Vn minus V0 will still go here, but these measures are outside of Ek, outside of the ball minus Ek. And using this, one can show that Vn plus W of Vn in fact goes to this almost everywhere. Well, we remove a bad set, and in a good set it is possible to show almost everywhere convergence. And now so we have this. And now by the diagonal procedure, we can have a subsequence which goes to V0 plus W0 almost everywhere here, because the measure of the set J is 0. And now, well, we have a ball BR, so once again we make a diagonal procedure, and we obtain convergence almost everywhere in R3. And finally, this is quite easy one show using the minimizing properties that W0 actually has to be W of V0. And now the functional J of U can be written in this way. We take, well, curl U is equal to curl V, which is equal to the gradient of V. And we have V plus W, U equal to V plus W. And now J is of class C1, in fact, and critical points of J will be solutions to this equation. And now let me introduce the generalized Nahari manifold or the Nahari-Pankov manifold. We take u in x with w removed, and we have j prime u equal to 0 as for the usual Nahari manifold, and also j prime u w equal to 0 for all w in the space w or in the subspace w. Also, one can rewrite this in that form. Well, this is nothing else than j prime u equal to 0. And also, after some easy manipulations, one can show that this is equivalent to the divergence of this is equal to 0. So now, by recent results by Mederski, Skina, and myself, one can show that if the infimum is attained, then the minimizers are ground state solutions to the equation. Well, there are some non-trivial points here because we don't know if n is of class C1. Now also we have that u is in n if u is equal to this. Well, if we take w equal to w of v, then we get this equality. And now we take the infimum over O, maximum over OT bigger than 0 for this expression. Now we have S curl equal to this, as I wrote down earlier. And curl u may be replaced by the gradient of v. And here we can have v plus w of v instead of that. Also, another way of expressing this is that S curl is equal to the infimum over O v and maximum t bigger than 0 over this quotient. And also one can show that the infimum over n of j is equal to this. And therefore one needs to show that the infimum of j is attained. So if we take a minimizing sequence in n, so by Ekland's variational principle, one can assume j prime un goes to 0. One sees this is bounded. And passing to a subsequence, one has that Vn plus W of Vn goes weakly to this in X and almost everywhere. And using this almost everywhere convergence, well, this is in fact, this is a crucial point where this is necessary. Using this, one can show that V plus W of V is in fact a solution. Now, so if Vn goes to 0 in L6, then Un will go to 0 in L6, and one has J prime Un equals to this. This is little o of y, so Vn goes to 0, and one shows that also J of Un goes to 0. But this is a contradiction because we know that S curl is, at this point we know that S curl is bigger than or equal to S. And now we can make dilation by S and translation and dilation, translation by Y and dilation by S. Then there is a result of Solimini, which says that if Vn does not go to 0 in L6, and we know it doesn't, then one can find Sn and Yn so that this will go to weakly to some non-zero V. We have this, so assuming that Sn is equal to 1, Yn equal to 0, we have that Un goes weakly to U, which is non-zero, so U is a solution. And also, I will not discuss this. This is a rather known argument, which shows that U so obtained is in fact a minimizer. So the infimum exists, is taken by some function, and this function is also shows that S curl is attained. And now the question arises. We know that S curl is equal to S curl of omega. Can S curl of omega be attained on some omega which is not the whole of R3? Well, we don't believe it can. And to support this conjecture, well, if S curl is attained by some U, one can extend it by 0. So because of this equality, U will also solve this equation in R3. So if this were attained in some bounded domain, this would imply existence of ground states in R3 which have compact support. And well, we could not exclude this, but we don't believe this can happen. Now let me very briefly discuss a Bressis-Nierenberg type result. So we take curl U here, and here we take lambda U plus U4U in omega. Omega is a bounded domain with smooth boundary. In this condition, it's sometimes called a metallic boundary condition, because one can think of a domain which is surrounded by a metal, and the metal is a perfect conductor, so there is no electromagnetic field. So here, the solutions would be critical point of this function. Also here, this term is added. And, well, we still have the composition into V omega and W of omega. But in what follows, I will suppress the subscript omega. So look at this eigenvalue problem. Well, the first obvious eigenvalue is lambda 0 equal to 0. The eigenspace is the whole W or W omega, to be more precise. And the following is known, that V is contained in H1 omega R3, however, provided omega has sufficiently smooth boundary. If the boundary is not sufficiently smooth, in fact, there are examples where V is contained in H1 halves, but not in H1. And when we have divergence V equal to 0, so on V, we have this eigenvalue problem, and therefore there exists an infinite sequence of eigenvalues. And now take lambda between two eigenvalues. And now V can be decomposed into a positive definite part and a part which is a negative definite. It is spanned by k-1 first eigenvalues. Here n lambda is, well, it's, well, there is a certain difference compared to n which we had earlier, but the idea is more or less the same, and we have c lambda, which is the infimum over n lambda. And now I need to define S curl bar, the largest constant c, for which this holds. And note that here I don't, well, when I defined S curl, I had R3 here, and I took all W which are curl free in R3, not in omega, so that's the difference. This, in fact, is more natural, but S curl is easier to work with. For S curl bar, we were only able to prove this inequality. And now we have a theorem that if k is bigger than or equal to 1 and lambda is in this interval, then this Bressis-Nuremberg-like equation has a ground state solution. And moreover, if lambda approaches lambda k, then the ground states go to 0. So this is a kind of bifurcation. Well, what happens between lambda k minus 1 and this, we don't know. There may or may not exist solutions. And the key facts here are that, well, first of all, the Palais-May condition holds if C lambda is less than C0, and C lambda is certainly less than C0 when lambda is bigger than that. This is why we need this bound. And now I would like to mention a few open problems. Well, first, I mentioned some of them. First of all, does there exist a ground state solution whose support is a proper subset of R3? As I said, we suspect the answer is no. Also, another thing, can one find an explicit expression for a ground state? At least, can one say something about the decaying properties of ground states? Next question. Do the solutions to this equation have any symmetry properties? How regular are they? We don't even know if they are continuous. Well, one should guess that they must be radially symmetric, but there is a paper by Barge and others which shows that if one takes, well, for this particular equation, if one takes radially symmetric solutions, they must necessarily be trivial. There is still a possibility that there are cylindrically symmetric solutions, but certainly not radially symmetric. And next, is S curl bar equal to S curl for good domains? Good domains, I mean sufficiently smooth boundaries. And can there exist well, for really bad domains, we don't even know if S curl bar is bigger than or equal to S. So can it be smaller than S for some singular domains? And this is my final slide.
Okay. Thank you, Andrei, for the nice talk. It's a very interesting subject. And let me see if you have some questions. Let me see here. Comments. Okay, there are some comments here. Gustavo put here in the stream. But I have a question, Andrei. What you can say about multiplicity of solutions?
Well, for the critical exponent problems, the answer is very simple: nothing.
So there is something to do.
Yes. It's one could, in principle, think that if one knows a little bit more about ground states, one could try to look for multibumps, but without knowing anything, it's unclear if this is possible.
Okay. Let me see if we have more questions. I think that we don't have any questions. I would like to thank you again for this talk, for taking part of our event. And I hope you can meet person as soon as possible here in São Carlos or in Stockholm. Who knows? And
well,
I would like. Okay,
well, sometimes I think the virus will go, so we will be able to resume traveling.
Yes. We have to take the shot first. I would like to thank the audience for attending the webinar, and we will resume tomorrow at 9 a.m. São Paulo local time. Hope to see you tomorrow, and thank you very much, and bye.
Thank you.